This is section 1.5 where we talk about probabilities of intersections. So first we're going to discover the general multiplication rule, and we do this by looking at our conditional probability formula, which we used in our last section. And what we'll do is we'll just rearrange this to try and solve for the probability of A intersect B. So we want to find the probability of A intersect B, and to do this we can just multiply both sides by the probability of B. So we'll have the probability of A given B times the probability of B. This is what we call the general multiplication rule. So if you want to find the probability of A given B, A and B, A intersect B, you do the probability of B given A times the probability of A, or probability of A given B times the probability of B. The way I always remember this is you always do your conditional probability, whichever conditional probability you know. Sometimes you'll know one and not the other, and you times it by the probability of what was known. So probability of B given A times probability of A. So this A is what you actually know in your conditional probability. Let's see how this works. Jim and Mary are married. The probability that Jim watches TV after work is 0.6. Now as you do these problems, it's important that as you read the problem, you write down what it tells you. So probability that Jim watches TV is 0.6. The probability that Mary watches TV is 0.5. So notice both of these is just saying one or the other. There's no ors, ands, if. So it's just probability of Jim 0.6, probability of Mary 0.5. The probability that Jim watches TV, given that Mary does, is 0.8. Notice here now we have a given. We also have a Jim and a Mary in there. So read this and think to yourself, does this sound like an or, an and, or a given, or an if-then? Okay, so this was a given, so that means it's conditional probability. The hardest part here is make sure you write it in the correct order. So Jim watches TV given that Mary does. So the given part is what comes last, and what you're curious about is what comes first. So they're saying if Mary sits down to watch TV, then Jim has an 80% chance of watching with her. So if we know that Mary's watching TV, there's a 0.8 chance that Jim watches as well. Now number one, what is the probability that both Jim and Mary watch TV after work tonight? Well, anytime you see an and, that means an intersection. So Jim and Mary. So let's remind ourselves that and means intersection and or means a union. So if we want to find the probability here for an intersection, we need to use the general multiplication rule, which says use a conditional probability. We only know one conditional probability, so we better make sure we use that one. Times, and then you make sure you times by whatever was known in your conditional. So the known is what comes second, so you need times it by the probability of Mary. So probability of Jim given Mary was 0.8. Probability of Mary watching was 0.5. This gives me 0.4. So there's only a 40% chance that both of them will watch TV tonight. Now, what is the probability that Mary watches TV tonight if Jim turns it on and sits down to watch? Notice that if, that tells me we're working with a conditional probability, or we want to find a conditional probability. So they're saying we know Jim is watching. Now what's the probability that Mary does? So that means we know Jim, and now we're looking for the probability of Mary. Anytime you want to find a conditional probability, you have to go back to that original conditional probability formula, where you do the probability of the and or the intersection over the probability of what's known. So Mary and Jim, that's what we just found up above. Notice it doesn't matter if you say Jim and Mary or Mary and Jim. And that means the exact same thing. So it's 0.4. Probability of Jim is 0.6. So our answer is 0.6666. And finally, what is the probability that Jim or Mary watches TV tonight? That or means it's a union. So probability of Jim or Mary. Well, when you want to find the probability of union, you start off and say, okay, well, what's the probability of Jim plus the probability of Mary But then you remember for unions, if this was A and this was B, and you add up all the probability of A and all the probability of B, what happens? You double count this middle part twice. And you don't want that, so then you subtract out the middle part, or the intersection, so you don't have to worry about counting it twice. So we'll do probability of Jim plus probability of Mary minus the probability of the intersection. So this is 0.6 plus 0.5 minus 0.4, or 0.7. So 70% chance that one or the other or both watches TV tonight. Okay, now these next ones, we're going to use less formulas and a little bit more logic. So there are 4 blue, 5 red, 1 green, and 2 white marbles in a bag. Assume that after we draw a marble, we don't put it back before we draw a second marble. When you don't put it back, we call this without replacement. And knowing that we don't put it back is definitely going to change our answers. Okay. Let's see. One of the things you should always do is you should find the total of how many marbles we have. So we have 4 blue, 5 red, 1 green, and 2 white. So that would be 12 total. So we want to find the probability of blue and then the probability of white. So and really means intersection. But sometimes if I'm doing these, it's easier for me to think in words and than it is to think in upside down U's. So probability of getting a blue and then getting a white. So we're looking for the probability of an intersection. So technically, this would be the probability of blue times the probability of white given blue. Now, if you look at this, that would technically be blue times probability of white given blue. That would just give you the probability of the intersection of white and blue. So that's our technical. But for me, it's difficult to see these and then write it in the technical definition on these. And I can do these just by logic much easier. Okay. Do you notice though that I put the part that was given was the part that came second? And that was the probability that I multiplied it by. But these you can just do logically. So you want the probability of a blue. So first you'd say, okay, well, how many blue marbles are there? There are 4 out of 12 blue marbles. And always means times. So and you're going to multiply. Or you're going to add. Okay, so times, and now I need the probability of getting a white one. But here's where you have to pay careful attention. Because I want a white one, there are 2 white ones. But how many marbles are there now? We already drew 1 blue marble. So now there are only 11 blue marbles left. And this is 0.0606. Okay, so again, you find the probability of a blue and then the probability of white, but keeping in mind that you already drew 1 blue marble out and you did not put it back. Okay. Now number 2, let's find the probability of blue and then blue. So to get a blue would be 4 out of 12. Then I want another blue one. But I've already taken 1 blue one out, so how many blues are left? Only 3 blue and only 11 marbles. So 0.0909. Our next example, what is the probability of drawing a card from a standard 52 card deck and having it be red and hearts? Okay. So again, this one you can just do by logic. If you want red and hearts, that just means how many red heart cards are there in the deck. In a deck of 52 cards, you have 13 red hearts. So 13 red hearts out of 52 total. So 1/4. Now you could do this with our actual formulas. So the probability of red and hearts. I'm just going to do an H there. So probability of red and hearts is you have to do a conditional probability. Now in this case, which conditional probability do we know? It doesn't actually matter. You could pick either one. So let's do red given hearts. And then I would have to times it by the probability of hearts. She always times it by the probability of what's given. Okay, so this conditional probability, red given hearts. So this says, if I know it's hearts, what's the probability that it's red? Okay, so if you think about it, if you know it's hearts, all hearts are red, right? So if you know it's hearts, the probability of it being red is 1. The probability of hearts, well, how many hearts are there? There are 13 out of 52 hearts, so our total would be 1/4. And you might wonder, okay, well, what if I had picked the other conditional probability? Well, let's try it. So probability of hearts and red. Now, again, it doesn't matter what order I write those in. But let's do hearts given red. And then I would have to times it by the probability of red. Okay. So if you know it's red, what's the probability that it's hearts? So out of red cards, how many of those are hearts? There are, let's see, half of 52 is 26. There are 26 red cards, and half of those, are 13 of them, are hearts. So if you know it's red, you have a 13 out of 26 chance that it is also hearts. And what's the probability that they're red? How many red cards are there in the deck? There are 52 cards. Half of them are red, so 26. And this gives you 1/4. Now you might have also thought of this as both of these probabilities being 1/2, and you would have been correct as well. This next one, we want to find a probability for a three-way intersection. Most of these we'll just do with logic, but you could actually write out the formula. So if you want to find the probability of A and B and C, okay. Well, it says let's start with the probability of C given A and B. So we'd have to do the probability of C given A intersect B. But then you have to times it by the probability of what's given. Not an equals, times the probability of A intersect B. So technically that would be right, but this probability of A intersect B, maybe I don't know that. So we can write the probability of A intersect B as probability of A, well, let's keep the same order, let's do the B. Let's do probability of B given A times probability of A. And so our big long formula would be probability of C given A intersect B times probability of B given A times probability of A. Now if you had to, you could use this formula, but again, most of them we're just kind of going to do by logic once it gets this big. Okay. Or you could see an official rule, so A1 intersect up to AN would be the probability of A1 times probability of A2 given A1 times probability of A3 given A2 intersect A1, etc., all the way up to the end. Okay. Here's how you do it with logic. A license plate has 6 symbols. The first 3 symbols are letters from the English alphabet, and the second 3 symbols are numbers 0 through 9. A symbol cannot be repeated. What is the probability of having a license plate that says Gen 1, 2, 3? So sometimes I'll kind of write out what I'm looking for. So I need a JEN 1, 2, 3. Okay. Notice a symbol cannot be repeated, so that means again it's without replacement. Okay. So if I want to get a J, there are 26 letters in the alphabet and I want one J. Okay. Now I want a J and an E and an N and a 1, so I'm going to multiply all of these. Okay. Now I want an E, but I've already pulled out a J, so how many letters are there left to choose from? Only 25. And for an N, I pulled out a J and an E, so there are only 24. Now I want a 1. There are 10 numbers to choose from. But if I want a 2, I've already used the 1, so there are only 9 numbers to choose from. And for the 3, there are now only 8 numbers to choose from. And if you put this in your calculator, it's going to be about 8.9 times 10 to the negative 8. If you don't remember scientific notation, this would be a great time to go watch a video for it. I'm going to post links to probably some videos on basic math skills if you need to go check them out. So this would be scientific notation. Next, we're going to learn about what's called independent events. Okay, so two events are independent if they do not affect each other. What this means is that if A and B are independent events, then the fact that B has occurred does not affect the probability of A occurring. So this would be something like, if I was going to draw a card and roll dice, the fact that I rolled a 6 on one dice is not going to affect which card I draw from my deck. All right, so those are two things that would not affect each other. So A and B would be independent if, so these are our technical definitions. They're going to be independent if the probability of A given B is just equal to the probability of A. So this means that knowing B happened does not change the probability of A. Okay, so probability of A, if you know B happened, is still equal to the probability of A. Or similarly, the probability of B, if you know A happened, is not equal to the probability of B. And if they're independent, you should be able to check either one of these. And if they're equal, you know they're independent. Let's try an example. In a soft drink taste test, each of 1,000 customers chose between two colas, Cola 1 and Cola 2, and stated whether they preferred their cola drink sweet or very sweet. Unfortunately, some of the survey information was lost, okay, and the following information remains. So 683 consumers preferred Cola 1 to Cola 2. So for this, you have to kind of go through and say, okay, so this is the probability that they like Cola 1 is 683 out of a total of 1,000. And I have a nice little table for us to organize things. So Cola 1, the total number of people that like Cola 1 was 683. 620 consumers preferred their cola sweet. So the probability of sweet would be 620 out of 1,000. So all the total for sweet is 620. 85% of the people who like their cola sweet preferred Cola 1 to Cola 2. Let's see, so 85% of people who liked it sweet. So you do 0.85 times the number of sweet people of 620 is 527. So 527 people who like Cola 1 and sweet. Let's just make a note here. So how did we do this? So we had probability of people who liked it sweet. So we knew that they liked it sweet, preferred Cola 1. So Cola 1. So Cola 1, if you know it's sweet, and then we times it by the probability of sweet. That's what we did up here to get the probability of Cola 1 and sweet. Okay, but now that we know that, that's 527. So the people that like Cola 1 and sweet was 527. Now your total, grand total for everything is 1,000. Now that you have this much in your table, you can go through and find all the rest of the numbers by subtracting. Okay, so 527 plus whatever's here should add up to 683, so we'd have 156. 527 plus something is 620, so if you subtract those, you get 93. Let's see, 620 and 1,000, if you subtract that, you get 380. And by that logic, we can get 224 and 317. So we filled out the entire table. And we'll do different problems with a table like this where you have one variable and then another variable. So let's find the following probabilities. Find the probability that someone likes Cola 1. When we did that up above, we had 683 out of 1,000. Okay. Or you could look at your chart and say, who likes Cola 1? Cola 1 would be 683 out of a total of 1,000. So 0.683. Next, we want the probability that they like Cola 1 if we know that they like it sweet. We already actually wrote that up above, but let's see how you could do this just based on the table. So you would, to do a conditional probability, you always do the probability of the intersection or the AND part over probability of what's given. are known, which is they like sweet. So you come up here and you say, what's the probability of the intersection? So C1 and S, that's where they intersect, so 527. And probability of sweet, you find all the total sweet people, or 620. Okay. Now I actually skipped a step here. This, it said probability, so it would be 527 out of our total of 1,000. And down here it was 620 out of a total of 1,000. But those thousands will always cancel, and sometimes you go just straight to 527 out of 620, or 0.85, which is, again, what they told us in number 3. So let's see what I have written here. The probability of someone liking cola 1 is 68.3%. But if we know someone likes sweet cola, the probability of them liking cola 1 is 85%. See here? Probability of cola 1 was 68. Probability of cola 1, if you know they like it sweet, is 85. So that means knowing that they liked it sweet changed the probability of cola 1. So they affected each other. Okay, so because the probability of cola 1 given sweet and probability of cola 1 are different, we know that the probability of the event cola 1 is influenced by whether the event S occurs. Or we know that whether or not they like cola 1 is influenced by whether or not they like their cola sweet. So that means that our two events are dependent. They affect each other. So let's now try, what's the probability of cola 2 given sweet? Okay. So we would have to do the probability of cola 2 and sweet over the probability of sweet. Okay, so for cola 2 and sweet, you come back up. Which one has cola 2 and sweet? So that would be 93 out of 1,000. And probability of sweet is 620 out of 1,000. Which gives me 0.15. So what does comparing now probability of cola 1 given S and probability of cola 2 given S tell us? Okay, so let's see. Probability of cola 1 given S, which is 0.85, means if they like sweet cola, there is an 85% chance they like cola 1. Okay. And similarly, probability of C2 given S being 0.15 means if they like sweet cola, there is a 15% chance they like cola 1. Okay. So what would this tell us? Okay, this tells me that if people like sweet cola, because all of this is if we know they like sweet cola, they're much more likely to like cola 1. 85% of the sweet people like cola 1. So if you know someone likes sweet cola, they are much more likely to like cola 1. That also would tell us that they are dependent, that whether or not they like cola 1 and cola 2 is affected by whether or not they like it sweet. So we learned about independent events. Now we want to see, well, what would happen to our multiplication rule? So if A and B are independent events, then what would happen to this formula? The probability of A given A and B is equal to probability of A given B times probability of B. Well, what happens if you know that they are independent? So if independent, then the probability of A given B, say, well, we don't care if B happened, it's still just going to be the probability of A because they don't affect each other. So this turns it into the probability of A given B, or A and B, sorry, I keep saying that tonight, is the probability of A times the probability of B. This turns out to be a very simple formula. You don't have to worry about conditional probabilities. You can just multiply out your two probabilities. Now though, the very important thing you have to remember is this is only for independent events. So I actually had an email earlier this semester of someone saying, why can't I just multiply out these probabilities when they wanted to do it in an earlier section? And the answer is you can only multiply the individual probabilities if you know that your events are independent, which limits us quite a bit. So in example 32 though, let's try one where they are independent. So we have 4 blue, 5 red, 1 green, and 12 marbles, or 2 marbles, so that's 12 marbles again. So in other words, this is the same problem we already did once, but we're going to change it just a little bit. Assume that after we draw a marble, we put it back and then we draw a second marble. So what does this tell us? If we put it back, this is considered with replacement. And it means if you put a marble back before you draw the second one, are your 2 marbles affecting each other? No, they won't affect each other because you put the first one back. So your marbles would be independent. So let's find the probability of blue and then white. Because they're independent, you can just do probability of blue times probability of white. Okay, but again, I usually don't write these out in these kinds of problems. I just kind of think about it, do it in my head, or use the logic. So if I want a blue marble, there are 4 out of 12 marbles that are blue. Then I want a white marble. So there are 2 white marbles, but how many are there total? I pulled out a blue, but then I put it back, so there are still 12 marbles. Or if you think about it, this was the original probability of blue, this was the original probability of white. We didn't have to change them because, again, they were independent. So 0.0555. So notice that did change our probabilities from what we got before when we didn't put the marble back. And if we want probability of blue and then blue, well, first I would have 4 out of 12 blue marbles. But then I put a blue marble back. Now I want another blue marble. So I would still have 4 out of 12, which is 0.1111. Okay, sometimes I will ask you to show that events are independent. There are 3 different mathematical conditions that we can check, and if one of them holds, then all the others will hold. Okay? So if you want to check if they're independent, you can check any of these. You can check that the probability of A given B is still the probability of A. So in other words, we don't care that B happened. Or similarly, probability of B given A is equal to probability of B. So again, if you know that A happened, it doesn't change anything. It's still just the probability of B. Or you can check the probability of the intersection. So you find the probability of the intersection. You also find probability of A times probability of B. If it's the same, then you know your events are independent. Let's use that in this example. So below we have a summary of gender and types of jobs at a certain university. We want to know, does your gender affect which type of job you get? So we're asking, are they independent? Okay. Again, I can check any of those conditions. Let's just pick one. So let's say, is the probability of what job you get dependent on your gender? Okay. So let's pick a specific job. Let's pick faculty. And let's pick a gender, let's say male. Now you could pick any other job and any other gender, and this would still work as long as you do all your calculations correctly. So we want to find the probability of faculty if you know you're male. Okay. So this would be the probability of faculty and male divided by probability of male. Okay, so let's come over here and look. So faculty and male would be where they intersect, so 110. And since it's a probability out of our total of 300. And males, total males are 200 out of 300 faculty. And this gives me 0.55. So this says if you're male, you have a 55% chance of being faculty at this university. Now, probability of faculty, let's look at that one. Probability of faculty, there's a total of 120 faculty out of 300 people, so 0.4. So what does this tell me? If I was to write this out in words, it says, if you are male, there is a 55% chance you are faculty. But overall, there is a 40% chance you are faculty. So what does this mean? This means if you are male, you have a higher chance of being faculty. Okay, so does this sound like they'd be independent, not affecting each other? No, this sounds like gender is affecting instead of faculty, we'll say which job. Okay, so they would be not independent. Now, I say gender is affecting job. Technically, we would just be saying they affect each other, but logically, you're not going to change your gender based on which job you get, so it must be your gender affecting the job. Okay, so these are, again, not independent. When you say it's not independent, that's called dependent, meaning they affect each other, because we checked, and probability faculty given male is 0.55, probability faculty is 0.4. They are not equal. So we checked one of these, and they were not equal, so we say they are not independent. So now we're talking section 1.5. We're going to do this extra page about the multiplication rule for multiple independent events. So if we have the probability for the intersection of events, now let's make sure we add in this word. This is only true if it's independent. Otherwise, we have to worry about conditional probabilities. So if we have independent events, A1 through N, so we have a lot of independent events, and we want to find the probability of the intersection. The intersection, again, being an AND, so we want the probability of A1 and A2 and A3 all the way up to 80 then. Well, all you have to do, if they're independent, is just multiply each probability. Makes it really easy. So let's try this. We have a license plate, has 6 symbols. The first 3 symbols are letters from the English alphabet. The second 3 symbols are numbers 0 through 9. A symbol can be repeated. Now, because it can be repeated, that means that if I get an A the first time, that doesn't affect what I can get the next time. So these are independent. What is the probability of having license plate that says Gen 1, 2, 3? So if I want a Gen, I have a 1 out of 26 chance of getting a J. Then I want an E. Now it doesn't matter what I got the first time because they can be repeated, so I still have a 1 out of 26 chance of getting an E. And again, because you can repeat letters, I have a 1 out of 26 chance of getting an N. Now I want a number 1, but we only have the number 0 through 9, that's 10 options, so we have 1 out of 10. For the 2, we have a 1 out of 10. For the 3, we have a 1 out of 10. And this would give me 5.68 times 10 to the negative 8th power. For our next example, suppose I have a 0.8 probability of correctly answering any multiple choice questions on a quiz, and there are 3 questions. Notice it's a 0.8 probability for any of them, so what I get on the first one shouldn't be affecting the next one. So these should be independent. Or they don't affect each other. And because it's multiple choice, one question should not affect the next question. So what's the probability that I get all the questions correct? So I want the first one to be correct. Okay, or I always like to write out what I'm trying to get. So I need to get the first one correct, and the second one correct, and the third one correct. Okay, so to get the first one correct, I'd have a 0.8 chance. The next one will also be 0.8, and the next one will also be 0.8. Because I'm looking for the probability of ANDs, I multiply them. So I get 0.512. Okay. Next, what is the probability that I get all the questions wrong? So this would be the probability. Let's do a W for wrong. So wrong, and wrong, and wrong. Well, what's the probability of getting 1 wrong? If we have a 0.8 chance to get it right, 1 minus 0.8 gives me 0.2. So we'd have 0.2 for the first one, 0.2 for the second one, and 0.2 for the third one, which gives me 0.008. And what is the probability of my answers being correct, wrong, and correct in that order? So I am looking specifically for correct, and wrong, and then correct. So correct is 0.8, with an and we times. Now wrong is only 0.2 and correct is 0.8. This gives me 0.128. Now our next one is, what is the probability that I answer at least one question correctly? Whenever you see this at least one, again, remember we need to use the complement. And in our case, the complement of at least one question is that they are all wrong. So the complement of at least one right is that they're all wrong. So the probability of at least one correct equals 1 minus the probability that they are all wrong. Or 1 minus the probability of wrong and wrong and wrong, which we found up above is 0.008. So 1 minus 0.008 should give me 0.992. And example 36. The probability that a person has a positive test result is 0.02. Assume that the results are for different people are independent. So that, again, they should not affect each other. So if one person takes the test, what is the probability of a negative result? So the probability of a positive equals 0.02. So then the probability of a negative would be 0.98. Now, if 5 people take the test, what is the probability that they all have positive test results? So we are looking for the probability of a plus and a positive and a positive and a positive and a positive. Now, anytime you're looking for the probability of an and, we multiply. So each positive has a probability of 0.02. So 0.02, 0.02, 0.02, 0.02, 0.02. Or I could do a shortcut of 0.02 to the 5th power, since I know I have to multiply them 5 times. And I get 0.00000000032, or 3.2 times 10 to the negative 9. Now number 3, if 5 people take the test, what's the probability that the results are in order? Positive, positive, negative, positive, and negative. So we need a positive, and a positive, and a negative, and a positive, and a negative. So a positive is 0.02, the next positive is still 0.02, then a negative is 0.98, a positive is 0.02, and a negative is 0.98. This should give me 3.76 times 10 to the negative 4. Let's see, and number 4, if 50 people take the test, what is the probability that all the results are negative? So we want the probability of 50 negatives. Or the probability of a negative, and dot, 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 and a negative. And we're going to have to do that 50 times. Well, just like, what did we do up above when we wanted 5 positives? We did the probability of the positives 1, 2, 3, 4, 5 times, and did 0.02 to the power of 5. So if we want the probability of these negatives, let's see. So for these negatives, it would be a 0.98 times 0.98, and I would have to do that 50 times. So 0.98 to the power of 50 is going to be 0.3641. And if 50 people take the test, what is the probability of at least one positive? So again, anytime you see that at least one, we need to use the complement rule, or the probability of at least one is always equal to 1 minus the probability of none, or in this case, none positives. And to get no positives, that would be the same thing as 50 negatives. So we're going to have 1 minus what we just barely found, so 0.3641, which gives me 0.6359. This is still part of section 1.5. We're going to talk about probability trees. You can use these for independent or dependent events, and it's just another way, it's kind of a visual way to do some of these problems, and sometimes this is easier than trying to actually work it out using some formulas. So we have the personnel manager of a large corporation gives an aptitude test to all newly hired employees in an attempt to determine the potential for a management position. Based on past results, the personnel manager knows that 70% of new employees pass the test and the rest fail. Okay. Among the new employees who pass the test, 60% will end up in a management position. Okay. So let's kind of write down what it's told me here. So we know that 30% of the new employees pass. So the probability of pass equals 0.7. Among the employees who pass the test, so this is saying you already know that they passed the test. Okay. And then 60% will end up in management. So the probability of management, if you know they pass, is 0.6. Among the new employees who fail the test, so this is saying, okay, we know that they failed. 20% will end up in management. So 20% end up in management. So I guess even if you fail, they're not giving up on you completely. So notice we have some probabilities, a bunch of conditional probabilities, and it's saying among all the employees that are hired and take the aptitude test, what percentage will end up in a management position? So now we're looking for probability of management. And I don't know about you, but we haven't really learned any formulas that let you take these conditional probabilities and get back to just probability of management. So this is far easier if we again do what's called a probability tree. So first you say, when someone gets hired, the first thing that happens is they take the test, and they can either pass or fail. And we said the probability of anyone passing is 70%, so 0.7. Now your two branches will always add up to 1. So if you have a 70% chance of passing, that means you have a 30% chance of failing. Okay, and then we say, okay, if you pass, you can still end up in management or not management. If you fail, you can still end up in management or not management. So let's see what some of these probabilities would be. Okay, so this 0.7 was the probability of our pass. And we found that up above. Then this pass and then end up in management, or this is saying this is the probability that if you know you pass, what's the probability that you're in management? We found that was 0.6. What else did we find? We found the probability you're in management if you failed. So if you failed, probability that you're in management would be our 0.2. And again, each set of branches always adds up to 1. So if you pass, the probability you're in management is 0.6. That means if you pass, the probability you're not in management is 0.4. And down here, okay, if you fail, you have a 20% chance of being in management, and that means an 80% chance, or 0.8, of not being in management. So what you do is you draw your tree diagram, and then you find all of the intersections. So if you want to find probability of pass and management, you multiply these out, because probability of management given pass times probability of pass would be the probability of the intersection. So if you multiply along the branches, you always get the probability of the intersection. So 0.7 times 0.6 is 0.42. Probability of pass and not management is 0.7. Oh, sorry, I wrote 0.4, but I meant 0.6. It's still 0.42. And then if you do 0.7 times 0.4, you get 0.28. And probability of fail in management is 0.3 times 0.2, or 0.06. And probability of fail and not management is 0.3 times 0.8, which is 0.24. Now you should double check. If you add all of these up, you should get back to what you do. That's just a good way to double check. So these were individual probabilities, conditional probabilities, and if you multiply them together, you get to the probability of the intersections. The reason you want to do this is now our final thing that they're asking for is what's the probability that you are in management? And so to do that, you come back and you find everything that has management and you add them together. So management would be this one and this one. And if you add those two probabilities together, you're going to get all the total probabilities of management. Or if you prefer, we could write it out. So probability of management would be the probability of pass and management plus the probability of fail and management. So that's kind of the official way, but you might not remember this formula. Okay, this is our law of total probability that we learned about in a few sections ago, but you probably don't remember it, which is what makes the tree diagram easier. So again, for the tree diagram, you find all the branches, and then you just go through and say, what's everything that has what I'm interested in? So probability of management is 0.42 and 0.06, which means that they have 48% of their company that is management. Okay, and then similarly, if a randomly selected employee is not in a management position, what is the probability that the employee passed the aptitude test? Okay, let's see. So probability, let's see, we know that they are not management. So not management, and we want to know what's the probability that they passed. That's kind of an interesting one, so let's see. So conditional probability should start with probability of the intersection. So we'll do pass and not management over the probability of not management. Okay. So again, this is why having everything up there makes it so easy. So we want the probability of pass and not management. Okay, so let's see. We want pass and not management. That would be this one here. So that's 0.28. Now we want probability of not management. So that one we haven't actually figured out yet. So for not management, you can come back up and you can say, okay, well this one has a not management. This one also has a not management. So I need both of those, 0.28 and 0.24. Or 0.28 over 0.52, which is 0.538. So if you're not in management, there was a 53% chance that you actually passed the test, you just didn't make it into management. Also, if you thought about it this way, you don't actually have to do it this way, but you could have. The probability of not management, since we needed that for our denominator, well, you could use the complement rule. That's just 1 minus the probability of management, which we found in part 1. So in part 1, we found the probability of management was 0.48. So that gives me 0.52. So if you thought about it, yes, you could have done it that way. Let's do 2 more examples about probability trees. Let's say we have a manufacturer of 27-inch bicycle rims has determined that a rim may have 3 types of defects. The diameter of the rim is not within the specifications, which we'll call D. The holes for the spoke attachments are not evenly spaced, S. And the rim has a visible flaw in the alloy surface of F. So when we have D, S, or F, those are our actual defects. Okay. And these types of defects are assumed to occur independently of each other, so they don't affect each other. Okay. Based on past inspection data, 4% of all the rims have a type D defect, 2% have a type S, and 6% have a type F. And a rim may have more than one type of defect. So if we were to draw a tree diagram, I'd start off and I could either have a D defect or a not D. And then whether or not I have a D defect, I could also have an S defect or not have an S defect. And similarly, if I started with a not D defect, I could still have an S defect or a not S. And then I could have an F defect or not F. And no matter what I had already, I can still have an F or not F. And when you're doing probability trees, because this is just a really kind of nice, easy, different way to figure out some complex probabilities. You go through and you say, what was the probability of D, getting a D defect? So a D has a probability of 4%, S has 2%, and F has 6%. So to get a D, that would be 4%. And then to not get a D, it would just be the complement of that, or 1 minus that is 0.96. To get an S, we said that was 2%, so 0.02, and not an S would then be 0.98. So 0.02 for S, 0.98 for not S. And then we go through for all the F's and not F's. An F had a 6% chance, so 0.06, and the complement of that is 0.94. 1 minus 0.06 is 0.94. So fill that in everywhere. So 0.06, 0.94, 0.06, 0.94, 0.06, 0.94. Now, what we do after you've done all of these, because these are usually our conditional probabilities, or in this case they're independent, so it's not truly, well, you don't have to worry about the conditional probabilities because they are all independent, but if you multiply along the branches, you always get the probability of intersection. So at the end, we'll find the probability of each intersection. By multiplying. So like along this first branch, we'd find the probability of D and S and F would be, and you multiply along the branches, so 0.04 times 0.02 times 0.06. 0.04, 0.02, 0.06 gives me 0.000048. And we can continue for each of these. So we can do the probability for my next branch would be D and S and not F. So D and S and not F would be 0.04, 0.02, 0.94. Okay, and this gives me 0.000752. And you can go through and do each of these. We're just going to multiply along the branches. I'm just going to write them in. So we have 0.0023510. Try these on your own, and you can pause it and try and see if you get the same results. 0.001152, 0.018048, 0.056448, and 0.88435. So these are the probabilities of each possible intersection. When you're doing a tree diagram, you do want to just find the probabilities of all of the intersections. And then we'll actually go on to our steps after this and try and figure out what they actually want me to find. But it's usually a good step to find all of your possible intersections. Okay. Using the information given above, what percentage of all rims that are produced will have only a type D defect? Okay. So come back up. We only want a D defect. So which branches can you go along that will have just a D? Well, we can't have an S or an F, so we want to go to not S and not F. Okay. If we went to not D, well, that doesn't have a type D defect, so we don't want to come down here at all. So the only branch that has just the D is D and not S and not F, which would be this one right here. So we were looking for the probability of D and not S and not F, which was 0.0368. And that one you probably could have done without the tree diagram. It would have been too hard, but the next one is much easier with the tree diagram. So what is the probability of getting a rim that has exactly 2 defects? So to do this, we'll come up and we'll go through and we'll circle every branch that has 2 defects. So we could go D and S, that would be 2, so then we'll do not F. So we want this one. And then if I did D and not S, I'd also need an F to get 2. So we can do this one. D, not S, not F, that would only be 1. No, okay. Not D, but S and F is 2, so that one would work. Okay. Not D, S, and not F, no, that's only 1. Not D, not S, and F is only 1. Not S, and not F is only 0. So we only have 3 choices that include 2 defects. So we'll add those together. So what you do is you find all of the choices that include what you want, and then you add them together, because they're all possibilities or different ways to get what you want. So you find all the ways to get what you want and add them together. So we get 0.004255. And finally, one finished rim is to be randomly selected for inspection. What is the probability that the rim will have at least one type of defect? Now, you should see at least one and automatically think of the complement rule. But if you didn't, the tree diagram does make this easy as well. So if you want at least one defect, go through and circle or underline everything that has at least one defect. So everything that has at least one defect would be everything but the bottom. So you add up everything but the bottom. Or we could use the complement rule. So the probability of at least one is 1 minus the probability of none. And again, if you look back up which one has no defects, it would only be this bottom one. So 1 minus our 0.88435 equals 0.11565. So about an 11.5% chance of at least one defect. Let's do one more. We want to draw 2 cards from a standard 52 card deck without replacement. Now, because it's without replacement, we know that's dependent because they do affect each other. We're interested in determining if the cards are hearts or not hearts. So you draw the tree diagram, and first you can either get a heart or not a heart. Then you draw another card, and your second card can either be a heart or not a heart, and heart or not a heart. Since that's all you're interested in is hearts or not, that's what we put in our tree diagram. Now, the first time you draw a card, if you want to get a heart, you'd have 13 out of 52 cards are hearts. And if you wanted to not get a heart, well, there are 39 out of 52 cards that are not hearts. Or you could do 1 minus 13 out of 52. But that changes for your second card. We did it without replacement. We don't put those cards back, so these probabilities change. Okay, so now I drew 1 heart out, so if I want to get another heart, I would only have 12 hearts and only 51 cards. For a not heart, well, there would still be 39 not hearts because I didn't actually draw a heart, but there are only 51 cards. Okay. Now, if I do a not heart first and then I want a heart, there would still be 13 hearts, but only 51 cards. And if I drew a not heart first and I want another not heart, there are now only 38 not hearts and only 51 cards. Okay. Then you come over here to find the probability of intersection. And to find the probability of the intersection, again, it's really easy. All you have to do is multiply along the branches. So if I want the probability of a heart and a heart, I multiply along, so it'd be 13 out of 52 times 12 out of 51, which is 0.0588. Now, probability of heart and not heart is 13 out of 52 times 39 out of 51, which is 0.1912. Probability of not heart intersect heart is 39 out of 52 times 13 out of 51, which is also 0.1912. And probability of not heart and not heart is 39 out of 52 times 38 out of 51, which is 0.5588. Now that we have all of those, now we go through and see what we actually want to find. So what is the probability of getting exactly one heart? So if you want to get exactly one heart, you go through and you say, which ones have one heart? This one has two hearts, this one has one heart, and this one has one heart. So these two combinations each have one heart. So we could do 0.1912 plus 0.1912, which gives me 0.3824. Now number 3, what's the probability of getting a heart on the second draw? So you go through, which ones have hearts on the second draw? This one has a heart on the second draw, and this one has a heart in the second draw. So you add up those probabilities. So 0.1912 plus 0.0588 is 0.25.